In October 2002, the mechanical era of the American highway came to a close. The Cummins N14, the most trusted diesel block on the interstate, was officially discontinued, forced out by new EPA emission standards, stemming from a late 1990s consent decree. The raw iron and fuel that built American trucking gave way to the era of exhaust gas recirculation, or EGR. Independent owner-operators did not just lose an engine line. They lost a machine they could rebuild in a truck stop parking lot. They traded a million-mile mechanical rhythm for flashing check engine lights, sensor failures, and mandatory software diagnostics. A decade earlier, that exact sound had meant absolute American industrial strength. The engine had not lost its pulling power. It had simply become illegal to build. But the real story of the Cummins diesel is not just the story of an emissions rule. It is the story of how an engine block taught American freight to trust a sound, and what happened when that sound became too expensive to keep. Every week, we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like.
And what happened when the market moved on. Subscribe if that history matters to you.
The story begins not with nostalgia, but with a specific place, in Columbus, Indiana, in 1919. In 1919, the American highway system barely existed. Freight moved by rail, and local delivery.
He should be here any minute with the paperwork.
Good, I don't want to wait around all afternoon.
For the first decade, Cummins Engine Company was not a highway legend. It was a financial failure.
The factory floor in Columbus produced small, single-cylinder stationary engines used on farms and on marine applications, built under license.
They were temperamental, they leaked, and they did not make Irwin any profit. To understand why the early Cummins companies...
At the time, if a machine moved, it was usually powered by steam or a gasoline engine. A gasoline engine, a power plant that relies on a spark plug to ignite a highly volatile mixture of air and fuel. But it was thirsty, and under the heavy grinding load of a commercial truck, its ignition system was prone to failure. The alternative was the diesel engine. A diesel engine, a machine that draws in only air, compresses it until it becomes superheated, and then injects heavy fuel so it ignites purely from the heat of compression, was incredibly efficient.
It produced massive pulling power and ran on cheap, low-grade oil.
But in the 1920s, a diesel engine was an enormous, static piece of iron.
It weighed thousands of pounds. It was bolted to the concrete floors of power plants or set deep into the bellies of ships.
It ran at a fixed, slow speed. It was entirely unsuitable for the changing RPMs, the jarring vibrations, and the... Plessy Cummins realized that if his company was going to survive, the diesel engine had to move. It had to become lighter, spin faster, and throttle up and down predictably like a gasoline engine. The engineering hurdle was the fuel system. Early diesels used cumbersome air injection systems to blast fuel into the cylinders. Cummins developed a mechanical system that metered and pressurized the fuel, using a single distributor pump, allowing the engine to respond to a throttle pedal.
By the late 1920s, the company was nearly bankrupt, and Irwin was ready to pull his funding. Cummins needed a stunt to prove that a diesel block could survive the American road.
In 1931, he installed a prototype Cummins Model U diesel into a heavy-duty Marion truck. He and a co-driver departed from New York City, aiming for Los Angeles. It was not a race for speed.
It was a physical argument about efficiency and endurance.
The truck arrived in California 97 hours later. The total fuel bill for crossing the entire United States was $11.22.
That number, $11.22, was a shock to the American freight industry. It proved that the fuel economy of a diesel could completely rewrite the operating costs of moving goods. But a publicity stunt does not build a company. An engine must survive where Americans buy, service, and depend on machines.
Purity Stores, a regional grocery chain, operated a fleet of trucks that had to haul heavy food supplies over the punishing grades of the San Joaquin Valley. Their gasoline trucks were burning tremendous amounts of fuel and constantly suffering from overheated engines and burned valves. At the time, if a machine moved, it was usually powered by steam or a gasoline engine. It was an engine with 6 cylinders arranged in a straight line, designed with the exact physical dimensions needed to slide into the engine bay of an existing commercial truck. Purity Stores took a chance and ordered the diesel engines for their Mack truck fleet. The results shifted the gravity of the trucking world. On the mountain grades, the Cummins Model H did not stall. It did not overheat, and it cut fuel consumption dramatically. The drivers realized they no longer had to constantly shift gears to keep the engine from dying. They could simply lean on the diesel's low-end pulling power. Purity Stores became the first major American truck fleet to adopt diesel power, proving that the high initial cost of a diesel block was easily erased by the fuel savings and durability on the road.
This early adoption by California fleets set the stage for the architecture that would define Cummins for the rest of the century. As the 1930s bled into the 1940s, the demand for highway freight began to swell. Truck manufacturers like Kenworth and Peterbilt began offering the Cummins Model H as factory equipment. The block, the massive cast-iron foundation that holds the cylinders and the rotating internal parts, was overbuilt. Designed with thick cylinder walls and heavy main bearings that could be overhauled and rebuilt indefinitely. In the years during and immediately after World War II, skilled engineers took the fundamental architecture of a foundational engine design and
They increased the displacement. Displacement, the total volume swept by the pistons inside the cylinders, which dictates how much air and fuel.
This new series, known as the NH, would become the bedrock of the American highway. The 855 cubic inch block was a massive, naturally aspirated inline six that delivered a kind of mechanical trust the country had never seen.
it was simple, it was heavy, and it could be repaired with basic hand tools in a dirt lot if necessary.
It turned Columbus, Indiana, into one of the most important manufacturing centers in the Midwest.
A factory town where foundries poured iron and machining lines cut steel to keep up with the demands of a growing nation.
By the late 1940s, the blueprint was set. The engine had proven it could survive the road. Now it had to prove it could build an empire. The true breakthrough for the enterprise did not happen on a single day.
It happened because the American map was being completely redrawn. In 1956, the Federal Aid Highway Act authorized the construction of the interstate highway system.
This was not just a paving project. It was a fundamental shift in how the country did business.
Before the interstates, heavy freight moved primarily by train. Trucks were largely used for regional delivery, navigating winding, two-lane state routes. The new interstate system meant a truck could run at 60 miles per hour for hours on end, crossing state lines without stopping for a traffic light. This new geography created a brutal mechanical problem. Fleet operators like Consolidated Freightways and Roadway Express, a gasoline engine running at wide-open throttle for 10 hours straight would eventually overheat, burn its valves, or suffer catastrophic ignition failure. Early diesels were durable, but they were often sluggish and produced heavy black smoke that choked out following traffic. The fleets needed a power plant that could deliver massive pulling power, survive continuous highway speeds, and keep fuel costs low enough to make the freight math work.
The innovators answered with the continued evolution of the 855 cubic inch block.
But the true engineering breakthrough that locked in American fleet trust was the fuel system. While other manufacturers were experimenting with complex, sensitive distributor pumps, Cummins perfected the PT fuel system.
The PT, or pressure-time fuel injection system, a uniquely mechanical design that uses a simple low-pressure gear pump to move fuel to the injectors,
while relying on the engine's own camshaft to mechanically slam a plunger down and create the extreme high pressure needed for injection, changed the reality of truck maintenance.
In an American fleet maintenance shop, the PT system was a revelation.
It meant a mechanic did not need to calibrate a fragile, expensive, high-pressure pump on a specialized, dust-free test bench. The system was robust, simple, and entirely mechanical. It was just gears, plungers, and fuel. If a truck was pulling a heavy load through the deserts of Arizona or the freezing winds of Wyoming, the PT system ensured the engine would, but as the trailers got longer and the loads got heavier, naturally aspirated engines began to run out of breath, especially at high altitudes in the Rocky Mountains.
Cummins solved this by fully embracing forced induction. They added a turbocharger.
A turbocharger, a device driven by hot exhaust gases that spins a compressor wheel to force more dense air into the engine, allowed the 855 block to burn more fuel and generate massive power without increasing the physical size of the iron casting. This birthed the legendary NTC series of the 855, including engines like the NTC 335 and the NTC 350. When a driver in a Kenworth W900 or a Peterbilt 359 downshifted to climb the Donner Pass, the turbocharger would spool up, emitting a distinct, high-pitched whistle that became the signature soundtrack of American trucking. The forced air translated directly into torque. Torque, the twisting force of the crankshaft, often felt as the sheer physical pulling strength of an engine.
Horsepower, a measurement of how quickly an engine can do work, dictated the top speed on the flatlands.
But torque was what kept the freight from rolling backward. The mechanical brilliance of the Cummins 855 was not just in how it ran, but in how it was repaired. The engine was designed with wet sleeves. Wet sleeves, removable, replaceable cylinder liners that sit in direct contact with the engine coolant. When a conventional engine wore out its cylinder walls, the entire block had to be pulled out of the truck, sent to a machine shop, bored out, and fitted with oversized pistons. It was an expensive, time-consuming process that kept a truck off the revenue-generating road. With a Cummins wet sleeve block, a mechanic in a regional truck stop in Ohio or a fleet garage in Texas could simply drain the coolant, pull the cylinder head. In a matter of days, the truck had a completely rebuilt internal engine, perfectly within factory specifications, without the heavy iron block ever leaving the chassis.
This rebuildability completely changed the financial calculations of American truck fleets. The initial purchase price of the engine was an investment, but the total cost of ownership over 1 million miles was untouchable.
By the 1970s and 1980s, this combination of the PT fuel system, reliable turbocharging, and depending on the year and the specific market segment, over half of all heavy-duty Class 8 highway trucks sold in the United States were ordered with a Cummins diesel. Truck manufacturers like Freightliner, Kenworth, and Peterbilt built the trucks, but the fleets specifically requested the power underneath. The engine had bridged the gap from a risky alternative fuel experiment to the absolute standard of American freight. Drivers learned to tune the overhead valves by ear. Mechanics memorized the firing order. Fleet owners built their profit margins around the fuel economy. Cummins was no longer just an engine builder. In the American truck stop, the red paint on the block had become a currency of trust. By the late 1980s and into the 1990s, the Cummins 855 cubic inch architecture had evolved into its masterpiece, the N14. In an America where an engine could decide whether a field was cut, a truck made its delivery, a boat let the dock, or a generator carried a hospital through a storm,